In the real world, moist convection takes the form of showers, thunderstorms, and so forth. And these are quite interesting in their own right. And it's important to understand how they work, to understand how moist convection stabilizes the atmosphere, because it's somewhat different from the way dry convection does. So what we observe when we observe thunderstorms and showers is that they evolve through typically an evolution that we can kind of simplify into 3 stages. And it takes a typical shower or thunderstorm an hour or 2 to evolve through these stages. So in the beginning, air begins to rise from the surface where it's heated or moistened by evaporation from the ground or the ocean. And water vapor condenses into a cumulus cloud. But in the early stages, not enough time has elapsed for those small water droplets to coalesce into rain droplets. As the cloud grows taller and the liquid water concentration goes up, those small droplets coalesce into rain. Rain falls at a speed which is comparable to the speeds of updrafts. It's measured in meters or even tens of meters per second. Some of the rain falls into unsaturated air and begins to re-evaporate. That chills the air, makes it cold, negatively buoyant. And that cold air flows down toward the surface, bringing the low entropy of the upper troposphere down to the surface with it. And that cold air spreads out at the surface and eventually cuts off the supply of high entropy air to the updraft, and the updraft gradually dissipates. So the formation of these downdrafts limits the lifetime of these convective cells to typically an hour or 2. Thunderstorms are often observed as collections of these so-called cells. Here's a map, and I'll try to produce a better one for the course, but a map of the distribution of updrafts and downdrafts in a typical summer thunderstorm over continents, where you see cells in various stages of evolution. Here's a photograph of some convective cells. We won't have any copyright issues with this because I took it myself. I'm trying to be conscious of that. In the tropics, showing this sort of medium-sized cumulus cloud. How do we know it's raining? Well, for one thing, we have a rainbow. And it takes rain to make a rainbow. Ordinary cloud droplets are too small for that kind of refraction to occur. But we can also see rain falling out of the base of the clouds. Now, in states of radiative moist convective equilibrium, there are some features of the state that are worth talking about. It turns out the most advantageous way of transporting heat is for the clouds to be relatively widely spaced. So what we see when we look at radiative moist convective equilibrium is air rising up at speeds of a few meters per second inside these tall showers and thunderstorms that are widely spaced. Now, averaged over the whole system in a statistical equilibrium state, you can't have any net upward mass transfer. So in between the clouds, the air is sinking. Typically, it's sinking at around a centimeter per second, or 2 orders of magnitude smaller velocities than the in-cloud velocities, which tells you that the fractional coverage of these updrafts is of order 1%. So in radiative convective equilibrium, the convective clouds are widely spaced. Most of the air is, in fact, clear. And that's evident, again, in this photograph that I showed you before, where there are many, many regions where essentially no clouds at all, and especially the deep clouds are relatively rare, cover a small fraction of the area. That's quite unlike dry convection, where the amount of air moving up and the amount of air moving down are roughly equal. There's some other interesting properties of moist convection, besides the fact that the updrafts are widely spaced. In equilibrium, the turbulent flux of enthalpy from the surface, the relatively warm, moist air rising away from the surface and being replaced by relatively cool and dry air, in the net, that turbulent flux of enthalpy must equal the vertically integrated radiative cooling of the atmosphere. So in radiative convective equilibrium, most of the troposphere is actually warmer than its radiative equilibrium value and is therefore cooling radiatively, except for the boundary layer. You have a local balance, and I'll have to go into more detail about this. I'll probably rearrange this whole discussion here quite a bit before I get to the real one. But you have a balance that the mass flux carried by the convection times the vertical entropy gradient has to equal the local radiative cooling rate. The precipitation averaged over the domain has to equal the evaporation. Otherwise, water would be accumulating in the atmosphere. And as we've seen, the surface enthalpy flux is equal to the integrated radiative cooling, but most of the surface enthalpy flux over the oceans in radiative convective equilibrium is because of evaporation. So approximately, the evaporation rate is proportional to the radiative cooling. And as I've stressed to you before, the radiation and the convection are highly interactive. The convection lofts water, and that serves as the primary greenhouse effect that influences the radiative transfer.